Hello, my name is Mike Cohen, and this is my presentation of my Capstone project for IBM's Advanced Data Science Specialization via Coursera.org. My project is first and foremost about recipe popularity prediction, and its architecture is influenced by techniques from lots of different subfields of data science. It's got some natural language processing in it, some network analysis, a little bit of time series considerations, a tiny bit of deep learning, and it uses a lot of undersampling at the data level because we're working with a really imbalanced data set. So it's kind of a nice potpourri of techniques, I think, and I'm excited to show it off a little bit. For this capstone presentation, I've been asked to make really two presentations. The first is supposed to be a non-technical presentation for stakeholders in which I explain the main ideas of the project, the problem that we're trying to solve, and what the model does. And then the second presentation is supposed to be a more technical one with more details for other data scientists to be able to follow my work. So I'll launch right into the stakeholder presentation to begin. So the motivating question for this use case is, which online recipes have the potential to become popular over time? So a thing about food.com and about lots of other websites and social media platforms which host recipes contributed by users is that the vast majority of recipes will never achieve any meaningful number of interactions. They'll never become popular. So if you look at the images at the top of the slide here, poor Jimmy G's carrot cake has been on food.com for 20, 21 years. It's only ever gotten one interaction. So please go try this carrot cake. Similarly, Mary's hot and spicy sausage and cabbage soup has never gotten a review in its 20-year lifespan on food.com. So most recipes are just posted and then kind of waste away or fade into oblivion. So 39 of every 40 recipes posted on food.com, taken from our data set, which runs from about 2000 to 2018, have never accumulated even 25 user interactions, and 99% of them have never accumulated even 50 user interactions. Most of them are 1, 2, 3, 4, 5 interactions or 0 interactions. So the idea for the project is that if food.com or other recipe website proprietors were able to predict which recipes have a good chance of actually generating a lot of user interactions, then they can promote these recipes, give them to the marketing team, put links on the front of the website, and that's going to drive up user engagement and increase website traffic. So in order to give a concrete model of the problem, I'm setting a couple of initial parameters, which actually can be chosen by the user. So the first parameter is lowercase t1. That's the initial time parameter, and really we want to imagine that that's the present moment. I want to forecast starting right now and look into the future. And then time lowercase t2, as I mentioned, is some future time. Capital T is going to be a threshold for the number of user ratings. So our model is going to look at all the recipes and give an ordered list of which recipes are the most likely to cross that threshold of T many user ratings by future time T2. So the data sets that I worked with to build this model is recipe data scraped from food.com between January 20th, 2000 and December 20th, 2018. The data was taken from Kaggle.com. So the data consists of about 230,000 recipes, about 1.1 million user interactions. The recipe data basically has everything you expect to see on the website. It's got the title of the recipe, who wrote the recipe, when was it submitted, how long does it take to cook, how many calories does it have. It has all the text data, all the raw text of the steps of the recipe, of the tags on the recipe, typos and all. So it has all of that information that you would see on the website itself. So the solution that I built to this use case is a type of ensemble model, essentially a two-step ensemble model. The first step consists of a family of naive Bayes estimators, which work on text data from recipe reviews. So they look at the recipe, they aggregate all the reviews that it's accumulated over its lifetime, and then the naive Bayes estimators try to make a guess about how likely it is that that recipe is going to succeed in the future. And then the second step in the ensemble model is a simple logistic regression, which is trained on several key recipe features, which I'll describe in more detail in the technical talk quite soon. So what the model does is it looks at data available for the recipe at time t1, and it estimates the probability that the recipe will cross the threshold of T many user ratings by time t2. And because it outputs a probability estimate, we can sort from most likely to least likely and give a list to food.com of recipes that we think have a good likelihood of doing well and therefore food.com stakeholders can promote these recipes, try to push them, try to do something with that information. So some strengths and advantages of the model as it's built, in my opinion. For one thing, I think it's nice that there's the flexibility of the prediction parameters. So in deployment, we're always going to assume that T1 is the present day, but the stakeholder can choose the threshold T. What do we consider to be a popular recipe? Do we want to know which recipes are just going to get 10 interactions? Or do we want to know which one is going to accumulate 1,000 interactions, which of course might be a very difficult prediction problem. But there's some flexibility in building the model, choosing those initial parameters, and the prediction time can vary. It can be a long-term prediction or a short-term prediction. Secondly, the fact that the secondary or the final component in the ensemble is a logistic regression on a relatively small feature set, just a 13-dimensional feature set, means that it's going to be quite easy to test new potential features. If someone has an idea for a feature of a recipe that might be predictive of its popularity, it's going to be quick to engineer that into the model. Retrain the logistic regression takes a split second. You see whether it's improved the performance of the model or not, and then it's simple to implement the change in the model if it does improve the performance. At this point, we'll move on to a more technical presentation. I'll talk about some of the details of the architecture and the decisions that went into the model. So first I should talk about data quality and exploration. So the data exploration was conducted in Jupyter Notebooks using the standard data science packages available in Python. I should talk about the main things that I focused on in my data exploration and data cleansing. So the first thing that I want to talk about is that what we're doing is essentially a time series forecasting, right? We want to look into the future and ask which recipes are going to become popular. And so anytime you're doing time series forecasting, there's a great risk for data leakage. If I'm training a model which is going to try to foresee the future, then in order to train the model, I need to go back into the past and look at past information and train the model on past information so it knows when it's successful, right? It's a supervised machine learning model, so it needs to know when it's successful by looking backward. But whenever you're doing that kind of process, it's very easy, if you're not careful, to accidentally allow information here from the future to inform the model that you're supposedly training in the past, and then it overperforms, but it doesn't have that information when it comes to deployment. So this is the big risk, and so the main thing that I focused on early on was just making sure that all the data was organized by date, in order, and when I was building the training feature set for the models involved, that it's only using information which really would genuinely be available to it at the time of prediction. Secondly, the other major challenge in the project is that, as I mentioned, recipes actually becoming popular and crossing popularity thresholds is quite rare in practice. So looking at this data set with 250,000 recipes or so, if you want to know not only which recipes will gain, say, at least 50 ratings, but moreover, which are going to gain 50 ratings in the next year, so if you also put a time limit on it, then the proportion of recipes that cross the threshold gets to be about 1 in 2,000. So for every target case, every popular recipe, there's like 1,999 unpopular recipes. And so we have an extremely imbalanced prediction problem. So here's a little visualization of the imbalance problem. So I have two plots here. If you look at the top plot first, this is a scatter plot of all possible recipes on food.com between January 20th, 2000 and say January 30th, 2018. So 20 years worth of recipes, there they all are. The x-axis is the recipe age in days. How long has it been posted on the website? And the y-axis is what's the total number of user interactions that it's achieved at this point. So as you can see, down at the bottom of the plot, there's thousands, tens of thousands of recipes stuck in this swamp. Right, almost all of them have no interactions, 0, 1, 2, 3, definitely less than 10. The vast bulk of the data is laying in this thin swamp at the bottom. But then, as time passes, recipes get to be a couple years old, and then we start to see more and more recipes kind of bubbling up and somehow becoming popular over time. Second plot on this slide it's actually the same as the first plot, but it's just truncated. The y-axis is just truncated down to 100 ratings, so we can look down in a more reasonable ballpark and kind of see what's happening. So for the experimental run that's contained in the notebooks for this project, the target is set at 50. About 1 in 2,000 recipes will not only cross the threshold, but will cross the threshold over this 13-month interval. So the red tick marks in the second plot, that's the target data. Those are the popular recipes that not only are popular, but are going to become popular in the time interval that we're looking at. So some of the technical details of the model that I built, as I mentioned, it's an ensemble model with essentially 2 discrete steps. The first step is actually kind of a sub-ensemble. It's a family of naive Bayes classifiers, which are trained on the aggregated text data from all user reviews for each individual recipe up to the time of prediction. So it takes all the reviews that have ever been left, puts them into a giant bag of words, and then about 50 naive Bayes classifiers just look at that collection of words and try to make a guess. Is the sentiment good? Is the sentiment bad? Are we likely to become popular? Are we not likely to become popular? This makes the naive Bayes estimators train even faster, and it makes them much, much more sensitive to the minority class. They can sniff it out a lot better. Step 2 is a logistic regression, which is trained on 13 features. One of those features is the probability estimate given in the first step by the RUS boosted naive Bayes classifier. And the logistic regression as a second step, it hurts the recall a little bit, but it dramatically improves the precision. So this is the idea. Here's a list of the features on which the logistic regression is trained. The 9th feature is the probability prediction, which is output by the first ensemble model of naive Bayes estimators. So it's training on the previous prediction. The last 4 features I think are kind of interesting. These were identified in an academic paper that I came across called On the Predictability of the Popularity of Online Recipes by Tratner, Meslong, and Elsweiler, appearing in EPJ Data Science in 2018. So I looked through this paper, and these 4 features were identified as being strongly predictive. And I thought that they would be a nice excuse to use some additional packages, some natural language processing and network analysis. And so these guys are thrown into the model. The first one is what's called the instructions lick score. And I'll let you Google the definition of the lick score, but it's essentially a measurement of the readability of the instructions. The second one is the innovation IDF score. This is essentially an average rareness of the ingredient list. The last 2 features here, the innovation Jacquard score and the average innovation Jacquard score, these guys are conducted via a network analysis on the quite large network consisting of all recipes and all ingredients as the nodes. So this is a network consisting of about 250,000 nodes, and we connect an ingredient to a recipe by an edge if and only if the ingredient is included in that recipe. So we have a natural way of drawing edges between nodes, and so what we get is a quite large bipartite graph. And the way that we compute the Jacquard score is basically we want to look at 2 recipe nodes, and ask, do we think that these recipes are pretty similar? And the way that we compute that is we look at all the ingredients which are in either recipe, connected by edges to the 2 nodes that we're looking at, and we ask, of those ingredients, what proportion of them are contained in both recipes? In other words, what's the overlap, the ingredient overlap between these 2 recipes? Of course, that's called the Jacquard index, hence the term innovation Jacquard score. So you compute the similarity between any two recipes, and then basically the innovation Jacquard score is going to be 1 minus the maximum of all those Jacquard scores across all recipes. And so if you have a high innovation Jacquard score, it means that the recipe is quite unique. It's really unlike any other recipes on the website. Therefore, maybe it's more likely to succeed. This is the idea. So at this time, we can take a quick excursion to the engineering notebook, the feature engineering notebook. So it's organized into the 13 features. And a lot of them are straightforward, just pulling them out of the data. But the current number of ratings, the current mean rating, etc., this is time-sensitive information. As I mentioned, we want to prevent leakage. So there's a little bit of coding here just to make sure that we're measuring ratings and information about the recipe in the present day at the time of prediction. So essentially just some time series cleaning and organization. Step 4 is the RUS boosted naive Bayes model being trained. So here text data is aggregated using the natural language toolkit and cleaned up. And then we train the model on it. We vectorize the text into a giant sparse matrix and train the model on it. and we output these predictions for the training set and the test set. Then lastly, I would like to comment on the network analysis that I was describing, because for me, for my machine, or even for the machines on the cloud on IBM Watson Studio that I was using, a full computation of these Jacquard indexes for the entire network was too computationally intensive. It was impossible for me to complete. And so in order to make it computationally feasible, what I did as kind of a fix or a stopgap is I severely narrowed down the number of nodes that we're going to look at into basically two smaller piles, two small subsets of the nodes, one of which is going to be all popular recipes, the ones which already have achieved at least 50 ratings, and the other pile is going to be all candidate recipes. These are recipes which the random undersampling naive Bayes classifier predicts have a good chance of succeeding. And as we mentioned, that classifier has extremely high recall, so we're really not losing anything by trimming down to that smaller node set. And then basically we conduct the network analysis only on these subsets of the nodes. So the primary evaluation metric that I've chosen for this model is average precision. The definition is here on the slide. Average precision is closely related to the idea of the area under the precision recall curve. You can think of this as kind of the least optimistic estimate of the area, the least optimistic Riemann sum, trying to give you the area underneath the precision recall curve. This is a metric which is common for information retrieval problems. So you think about trying to evaluate a search engine where a search engine is given a query and it wants to return relevant results. But the first couple results are the most important ones. You want to know, are you getting good results at the top level? And then as you go further down the list, if you get fewer and fewer good results, that's not so important. It's kind of a top-heavy measurement of precision. So in the model definition and validation phase, I trained several different models, 4 different models. I focused on models which return probability estimates because I wanted to be able to order my list of results from most likely to least likely. So the models that I trained, a couple simple classical models, logistic regression, decision tree, a gradient boosted ensemble with decision trees as the weak learners. And then lastly, in fulfillment of the requirements for this capstone, I trained a very simple feed-forward neural network with one hidden layer, straightforward neural network. And these models were validated on the training data using a train test split. So I have test data which is set in the future. I'm reserving that for the final evaluation of the model. But going back into the past, we have our training data where we're trying to understand recipe popularity growth. And on that training feature set, we're doing train test splits to validate these models and compare them before making a final selection. Here we are in the notebook now. Here we are training a couple of simple classifiers, logistic regression decision tree, gradient boosted decision trees. And then here's the neural network being defined. And here's the neural network training. It's training and training, minimizing that loss function. It's looking good, looking good. Okay, it trained pretty quickly there. Okay, so now we have 4 models. And then we compare across a couple metrics, the average precision. I went ahead and looked at area under the ROC curve, even though it's not very meaningful in this context because the false positive rate is always going to be extremely low. So I didn't put a lot of weight on this metric, but I went ahead and computed it anyway. And then lastly, there's a decision threshold chosen to optimize the F1 score, and I took the recall and the precision at that particular decision threshold. And so we see that logistic regression comes out with an average precision of about 0.36. Recall is like 0.88, precision is like 0.27 at its optimized threshold. Scrolling down, decision tree does pretty poorly. It has an average precision of about 7%. The gradient boosted model is only a little bit better, about 17% average precision. The neural network really does quite poorly, average precision of 0.1%. So this neural network probably needs to be diagnosed, but maybe it needs to be trained on a different loss function or something. I didn't spend a lot of time diagnosing it because I felt that the logistic regression was already performing well, and it's the simplest model available. I hope that it's a sign of good feature engineering. That's the way that I'm interpreting it. And here's a quick graphic of the precision recall curves. As I mentioned, the average precision metric can be viewed as sort of an estimate of the area under the curve. And in this case, the blue zigzag curve looks like it has the largest area. And sure enough, it does. So finally, we'll move to the evaluation phase. I'll talk about the results. So the experiment, which is included in the notebooks, used the following parameters. As I mentioned, we take a threshold of 50 recipes for popularity, and we start trying to predict on December 31st, 2016. We look 13 months into the future and try to guess what's going to have happened by January 30th, 2018. And when we evaluated on the test set using this data that we've reserved, the average precision was basically the same as it was in the validation phase, about 0.35. Our model made about 87 guesses using its optimized threshold. It said, here's a list of 87 recipes that it thinks will become popular. And of those 87, 39 of them were correct for a precision of about 0.448. So quite good precision given it's such a difficult prediction problem. And the recall was okay. It found about a third of the actual recipes that will become popular, about 39 of the 123. In my opinion, this result is quite strong, given that it's such a rare target. We're looking for 123 target recipes out of 230,000. So it really is a needle in a haystack search, and I think to achieve an average precision of 0.35 is quite good. I want to conclude by talking a little bit about why I made the choice to do this ensemble model. Why did we do the ensembling? So initially, in the initial development phase, I was excited to attempt this random undersampling boosted naive Bayes classifier to attack the imbalance problem. That was really the original motivation from a technical standpoint. And what happened with that classifier is that it had quite good recall. It really did easily find all popular recipes, no matter what. But the problem was it was dramatically overguessing. Its precision was terrible, giving thousands of wrong guesses. So the model doesn't stand on its own. It doesn't provide a useful list. And so the second step in the ensemble, the logistic regression, is designed to fix that problem. And including the logistic regression improves the average precision by orders of magnitude. It goes from 0 to a third. So it's a pretty good improvement, pretty dramatic improvement. Now it's interesting to note that the logistic regression classifier actually by itself already does pretty well. And this kind of surprised me. So it turns out if you eliminate the probability estimates from the random undersampling boosted naive Bayes family and even remove the network analysis features, which were facilitated using the estimates of the naive Bayes family, if you take out those features, it drops the average precision of the model only by about 2 percentage points. So the logistic regression in and of itself is surprisingly effective. But I do think that the additional two average precision points, which come from the additional computations, I do think that that's a good, solid improvement. So I do think it's worth including the entire ensemble. That's it for my presentation of my Capstone project for IBM's specialization in advanced data science via Coursera.org. Thank you very much for taking the time to watch.